Okay.
I would, starting with number one, I've definitely like read in the notes in different places that sometimes when you have the AR1 structure for R, kind of, I don't know if saturated is the right word, but it kind of undoes any other effect, or like it accounts for it itself. And I guess I don't really know when to recognize that and whether that would be applicable to a question like number one.
Okay, so let's read this one. So consider basic science experiment. I do a lot of this research, because of where I work. We do a lot of basic science research here, where cell counts are measured at 4 time points from samples taken from individual subjects or animals. A linear mixed model will be fit for the data, perhaps after log transformation. That happens a lot, like with cell counts, you get right skew distributions. Fixed effects will be included for time, possibly treatment group, as well as their interaction. So we're focused on the ZB plus epsilon part of the mixed model. We're not as concerned about the fixed effects for this particular question. Determine the structure for V sub I, if random intercepts for subjects will be included. Actually, make sure I'm looking at the right thing here. Plus an AR1 structure. What does a combination of non-simple R and G allow you to do in modeling the covariances that using only one cannot do? Discuss in a few sentences. So in terms of, at least in terms of saturating the model on the covariance structure side of things, you do that by adding the unstructure to R. And once you add the unstructure to R, there's nothing more you can do in terms of flexibility in modeling the repeated measures. So here, by adding the AR1 to the random intercept, we're not gonna saturate the covariance structure. So you have 4 time points, and so you can look within one subject. You have your 4x4 matrix that you're going to end up with, and by putting it together and figuring out what V sub I looks like, you can compare that to the model that just has the AR1, and you'll be able to see, in particular, when you look at the correlation between 2 measures as time increases, you'll be able to see the difference between those 2 approaches.
Thanks. A follow-up to that is, say both models had the variance of epsilon in the same cell that I'm adding. Does it make sense just to say like 2 times variance of epsilon, or is it only counted once?
Can you ask that again?
Yeah, so let's say in the very first cell of a matrix, the VG or the GVG matrix has the variance of epsilon, so like sigma squared epsilon. And then in that same first cell of the R matrix, I have the same thing. I have epsilon squared, or sigma squared epsilon. If I'm adding those 2 pieces, does that mean in that first cell I have 2 times sigma squared epsilon?
Oh, you mean, so
just
you're
one?
talking about adding, when you add this piece with this piece, or?
Yeah, so I'm saying if it was in both G, Z, G, Z, and R.
Okay, so that they will have different parameters. So you're going to get in R you're going to have the sigma squared epsilon, and in G you're going to have they're going to be different variances. So when you add
Okay.
them, they won't be the same thing. So this is typically like your sigma b squared or something like that.
Okay.
So yeah, so by definition, we're not adding in the same variances in those two different pieces.
Okay. That clarifies a lot.
Okay.
Can I ask a general like homework grading question?
Sure.
I feel like I've been erring on the side of like only including exactly what the question asks compared to like my whole thought process throughout these questions. And I feel like I'm getting points off for not including more. So would you prefer us to include more, or does that make sense? Like for instance, like there were some examples where like I just wrote the null hypothesis, but I didn't put it into words. Would you prefer us to do like both those things or just one of them?
I have to
Does that
look
make
at the
sense?
specific question, but certainly, like, you shouldn't lose points for if you've answered it sufficiently. I guess that's the key question, the sufficient part. Like, but I'd have to look at the specific question that you have. I'm happy, Jan Ron and I will gladly look back at stuff, and I have don't ever hesitate to ask questions on, on those types of things. But if you can send me, like, if you can email me the specific, like a couple of specific examples, that might help me.
Okay.
I do like, in general, I like things streamlined as much as possible, because I feel like a lot of times people just, use the shotgun approach and say, well, I'll answer it like 10 different ways and maybe one of them will be right or something.
Yeah,
So I
that's
definitely don't want
okay.
to see that.
Okay.
But you're right. The question is like, what is sufficient and streamlined? Streamlined but sufficient,
Okay.
like enough, so that you should get full credit. So I could look at a couple examples if you send me those, or just send me the question. I guess we have that through Canvas. So just if you let me know that one.
Okay. I was just wondering in general. Thanks.
Yeah. So in general, again, streamlined, but usually I like descriptions to, like, if I say explain or something, make sure to include words too. But yeah, basic answer, and I'm happy to review stuff. Jan Ron and I can review either homework or quiz if there's, I know sometimes you're like, oh, I don't want to hassle with that, but don't worry about. I'd rather clear it up, and sometimes we change grades that way too. So there's no problem with that. Anything else?
We're ready to move on from 1. I have questions on 2.
Okay.
So I guess in this one, my thought is that we have to treat time as a class variable and only in order to use a random slope for it.
Yeah, let me get my bearings straight on this one. Okay, so we're going to have times be 0, 1, and 2, just as a simple example. Consider a model that includes a random intercept and so for time by subject. So here's the thing. like you can actually, whether or not you model time as class or continuous, you can think of what you do for your fixed effects as different from what you do in your covariance structure. And if you are to treat them differently, the way that you get around dealing with those differences is by creating two time variables. This is kind of an aside, but I think it actually may apply to one other question you have. So if you define a second time variable that's exactly the same as the other one, you can have one in the class statement and one not in the class statement. So you can model time as continuous, but then still use the class variable in the covariance structure statements that you use. But in terms of this specific question, if it's easier, yeah, I could just think of time as a class variable.
So then I guess regardless of what time you use in the main part of the model, when we're talking about the random effects, does that mean that we need a random slope for every single time point?
Oh, okay. Now, yeah, I'm thinking about the implications more about what you said. So actually, this is where you do that thing that I was talking about. When you say random slope for time, you are usually considering time as continuous. But if you treat it as a class, then you actually get a separate estimate for each time point. And you can do that if you want to, but that's not commonly what we do when we talk about a random slope for time. Okay, so yeah, so it is, you do have to think about these things for this particular question. I was thinking more generally, but here I think that we treat time as continuous. If we treat time as continuous, then what does your Z matrix look like? This will be.
You're gonna have your column of ones first, and then I'm thinking you would. I'm not sure. I'm thinking another column for each time.
Well, that would be if you have time as class, right?
Okay. So it would just be like 0, 1, 2 then?
Yeah. So we have yeah, so that's how I want you to do this one. Continuous time. You know, otherwise it gets pretty ugly. So this way you can figure out these what these covariances would look like. Treating time as continuous.
And when you compute those covariances, can you drop can you just restrict it to the random effects when you're doing that and drop the beta coefficients?
Yeah, so you don't need to, you're looking at the V matrix, right? And V is Z, G, Z transpose plus R, so you don't need to worry about the.
Oh, true.
So let's say, yeah, I mean, you could, again, you could treat time differently in the X beta part, but we don't need to worry about that to answer this. We just need to worry about the what Z, G, and R look like.
Okay.
So it's a kind of a matrix algebra exercise. You know, you have your Z matrix, and then what's the size of G for this?
2 by 2.
Yeah, it's a 2 by 2, and we're using the unstructured, which means that you're allowing a covariance between the intercept and slope. So G is a 2 by 2, and so when you do your V sub I, we know that, so Z sub I, this is 3 by 2. G sub I is going to be 2 by 2. Z transpose will be 2 by 3, and R will be 3 by 3. And just by including the random slope in addition to the random intercept, and allowing covariance, now we have a more complicated structure than just the compound symmetric. You know, like if you just add a random intercept, we know that we induce a compound symmetric structure. But if you have a random slope for time plus a covariance between those, then we have a more time-sensitive covariance structure.
If you were just, I don't know if I have a fully formed question. If you don't do unstructured in G, is that just and you just do independence, would that be the same as just 2 intercepts?
As it would be, no, it would, so you still have your, you know, your intercept and slope. It's just that then you're assuming that there's no covariance between where you start and the slope of that line, that those are independent of each other. So it's the same model. You have the same interpretations, you know, for the intercept and slope. It's just that you're not allowing a modeled correlation between those two elements. And so it'll be a little bit more constrained than the structure, but a little more flexible than the CF structure still.
I have just a logistics question on 3E. It just asked to do work with what we found as our optimal model in Part D. And I just didn't know if the models we're considering include the time as class or the 4th degree model.
I'm sorry, I'm going to have to ask you. I was going, as I was going to E, I lost track of your question. So
I was just wondering, when it asks you to use your optimal model from Part D, what models are included as our options? Like, are we just looking at the 1st, 2nd, and 3rd degree models, or can we also include the time as class model?
Yeah, it could be any of those.
Okay, thanks.
Let's see. Yeah, that's a good point. I guess given that there's some ambiguity to it, you do it either way. Like you can pick the best model up through the 3rd degree model, or you could use the class variable. So we'll make sure to, you know, to allow you full credit for either one. So you know, one of the points is that if you go up to the 4th degree, you actually get the same underlying model because you saturated the fixed effects. with the fourth degree model. So you should get the same AIC for that fourth degree model as you do for the time as class approach. And the question is, can you save a few parameters and get an even better AIC with a less than fourth degree polynomial? But one of the key things is, you know, in part D, you have to use method equals REML, you know, at least in SAS, in order to make meaningful comparisons. You have to use ML. You have to use the maximum likelihood method, because REML doesn't even have fixed effects in the likelihood. So it, you know, for model selection, that involves fixed effects, you should use method equals ML. But then you can go back to, you know, why do we use REML? The whole point is that we're trying to reduce, you know, underestimated standard errors, right? And that whole issue, what you divide by in the denominator. So for your final model, you can go back to that, to REML. All right, what else?
I don't know if it's been posted now, but I wasn't able to find the dog data on Canvas. But I actually had it from 6612, if anyone's taking that, but.
Yeah, maybe it's not up there yet. Let me double check. Yeah, so, I mean, don't hesitate to, sometimes this happens. Let's plop it in there. So, did you guys navigate the things pretty well on Canvas? I have gotten a little more advanced. I'm using the modules. Last year I just put everything in files and basically just went with that. But little by little, getting a little more advanced here. So data, yeah, it's not in there. So let me. So let's see, we have to do this real quick. So it's in files now. I think, you know, I'm typically trying to do CSV files or text files. I think CSV files if I can, you know, because I know that some people use R, so the CSV files are more portable. Anything else, guys?
I think one, and I don't know if we're going to get to this at some point, but kind of like Elise was talking, I think it was Elise was talking about earlier today. I think I have this big gap where missing data, and when you have 4 time points but times 2 and 3 aren't measured, or if someone skips a whole visit or something, like how that actually plays out in the model.
Yeah. Yeah, it's a good question. You guys asked really good questions today in class, and my short answer is that's one of the reasons why we index the matrices. Like I use R sub I because they may have different dimensions based on the number of follow-up times for subjects. And it gets really complicated when you have observational study data, because subjects could have different time points of measurement. They could have vastly different number of responses collected. You know, some could have 1 or 2 and others could have 10 or 12. So there's some data sets where, in fact, it's pretty common. Like I analyzed a lot of observational study data, and so just in general, you could have different time points, but yeah, it could be induced by missing data, like people don't come in for visits or things like that. And essentially what happens then is you create the R matrix and the V matrix just depending on how many measures a subject has. So if they came in for 3 time points, then their covariance structure would be a 3 by 3. If they came in for 5, then it would be 5 by 5. And then there's some methods that we talk about when we get to missing data, where we have what are the potential, like if they're supposed to come in for 5, then we separate out the ones that they were observed for and the ones that they were missing for. But that's kind of, you know, you think of that as a special case. I would say the basic answer is you develop the dimensions of the matrices based on the observed responses that you get for subject. And then you can find those, you know, in a complete data model.
So in that scenario, like, let's say you treat time as categorical, there's gonna be a bunch of people that don't even have one of the beta estimates. Does it crash your model for like the fixed effects or like polynomial trends? If someone only has 3 time points, but you're trying to fit a cubic because they're supposed to have 4, like what happens?
Usually it doesn't, unless there's a problem of like almost everybody missing a certain time point. You know, that's when you run into trouble. But if you have like combinations of, you know, group by time combinations that at least are pretty represented in the data, and that's usually the case, then usually you can get the model to fit and give reliable estimates.
You don't actually have to like add a row in with like, I don't know, I'm like logistically, you can just like have one person that only has 3 rows in your data and another person that has 5 rows in your data. You don't have to like put a missing time in for them.
No, as long as like if you're doing like a, especially like if you have, the short answer is no, that you don't have to add in, unless for some reason you want to like do the AR1 structure, and then you need to make sure that every subject has rows for every time point, and then you put in missing data. But an easier way to deal with that is to just use a spatial structure, you know, to allow for those types of gaps that you might have.
Okay, that makes sense.
And it's the same thing, like if you have, like you're collecting data over time, you know, like on weekdays, and you don't collect data on weekends. It's the same principle. You can just use a spatial power structure and not have to add in the weekend days. But if you use the AR1, which assumes that you're collecting on consecutive days, then you would add extra rows in your data set. I actually did that until I realized that, you know, I was doing a lot of extra work. This was many years ago, but, you know, and then I found that with mixed models, you can use spatial structures, they work fine. Actually with generalized estimating equations, GEE, there are situations where you do have to do that. You have to kind of fill out your data set. And we'll talk about that more later. All right, so so number 4 is pretty similar to what we talked about today with the mouse and tumor, but in that case, you know, you have school, and then the kid within the school. And then 3 measures. The first 2 kids have 3, and then the last has 2. Okay, so yeah, anything else you guys want to talk about? So I'm going to write down a few of the things. So it's missing data, impact on covariance structures. Let's see if I can pull up a few other things. Matt asked a question about the use polynomial trends, multiple comparisons. We talked about that. Was there anything else that we talked about? I think I, answered a lot of these, but sometimes I get additional thoughts too. Any other general questions you guys have? Well, if not, I'm gonna jump onto my webinar, and then feel free to email me or anything if you need to. And Jan Ran will have her office hours on Friday as well. Okay, take care, guys. We'll have a good rest of your week, and see you Monday.
Thank you.
Bye. Thanks.